I'm Austin Song, and this is my lab report for Lab 2 charge tapes. The purpose of this lab was mainly just to understand how to model lines of charge in GlowScript instead of just point charges, and through that we're able to understand how to use empirical lab data in combination with formulas to determine values for electric force / magnitude of a charge on an object. The fundamental principles for this lab are Coulomb's law and Newton's second law, respectively, knowing how to calculate the force of a charge on another charged object, and just the base force equation. So preview of the results, using the new multi-charge calculation for the line charge, the electric force was found to be 2.55 times 10 to the negative 3 newtons. And the magnitude of charge on the tape was 1.322 times 10 to the negative 8 coulombs. For observations, the system was the 2 charge tapes, surrounding was pretty much everything else, like the supports and the hands holding it, and measured values were separation when floating, tape length, and tape width, which we used in the code. The coded simulation, here we just established the measured constants. This function is for the E field. You just plug in a charged particle in observation location, and it calculates the E field at that location, just using Coulomb's law written out. This function basically creates a line charge. What's important is it needs all these variables to be initialized. Another important thing is that Q for each of the partial charges is set to the total Q over some arbitrary n that divides it into like the total number of charges in that line charge. And these two lines just create the line charge objects for the top tape and the bottom tape at their respective positions. So it's 0.26 for the x position, because it's 0.26 meters long, and the y position is 0.008 because that's the separation distance. E scale is just an arbitrary value to make sure the arrows are displaying properly. So is FE scale. FE on top is initialized as 0 because we're going to add the little FE partials onto it in this for loop. The for loop's the main important part. Basically what it's doing is it's iterating through each piece of charge in top tape and measuring the force electric field vectors at each of the positions on bottom tape on each position on top tape, and then adding them all up. So we call the E field function to get the DE at DQ top by DQ bottoms, all of the respective ones, it iterates through everything. And then in order to get the FE on top by DQ bottom, we multiply the partial E field by the partial top charge, and we add those respective values onto both FE on top and E at DQ top. So by the end of the for loop iterations, it'll have the total net force and charge on the top tape. Here it's just making the axis of the E at DQ top arrow equal to E scale times E at DQ top, just to get the alignment of the arrow correct. Middle top is just the middle of the top tape, the vector to that position. Again, here's just the FE arrow object that we make to display it. This is the FG arrow object that we make to display it. And it prints out magnitude of E force, magnitude of gravitational force, and then you can't see here, but it also prints out the magnitude of charge. The charge magnitude was determined sort of through trial and error, because this gives the E force for a given charge, but we know that since it's in equilibrium, E force has to match gravitational force. So I was able to plug in varying values of Q in order to make FE on top that was returned equal to the mg value. The code returns E force, gravitational force, and magnitude of charge. As you can see, the forces are pretty much identical, so they balance, and each of these is the partial E field contributions from the charges. For assumptions and errors, we assume tapes have equal charge distribution, air resistance is negligible, and lower tape is parallel to upper tape. These are errors because the tapes were not charged equally. The approximation only used 10 sort of DQ charges per tape, when in reality it's like an infinite line of them. Handling tapes caused loss of charge, and bending the tape when mounting impacted separation distance because they weren't perfectly parallel. So when modeling the tapes as a single point charge, the charge value you get for each of the tapes is much smaller than the charge value we got in this approximation. These estimates differ because the point charge approximation essentially centers all the charges at the closest possible distance versus the line charge model accounts for the distances between each of the partial charges from each partial charge on the top tape. So it'll give a slightly weaker force, which is more accurate because the charges are actually spread out across the tape. So this value is closer to the real value, and the charge value is much larger because the tape would need a much larger charge in reality to achieve that E force compared to the value we got when calculating a point charge, because the distances in reality aren't at that ideal center to center separation distance. That's it for my lab. Thank you for watching.